All right, so we want to kind of look at this shell method now. So let's just take a look first of all, and we'll look at an animation in a second. But let's just picture this purple region right here. The idea with the shell method, remember, is that now we are breaking this up into vertical rectangles. Okay, all of these purple vertical rectangles. And if I want to rotate this around the y-axis, then notice what I would have to do if I didn't have vertical rectangles and I just chose to use the disk method. In this situation right here, this piece right here, look at where my arrow is, that would be one radius that I'd have to use until I get up to this piece right here, to where from that point on, the left and right functions change. So that would be a situation where with the disk method, I'd have to do two different integrals. But what if we were to break this up into vertical segments like this, to where we end up having all of these vertical segments right here? Now, if I were to take that vertical segment and wrap it around, and I were to do that with each of these individual rectangles, then notice that I would have these concentric shells, basically, these concentric cylinders that would be filling up the region until I finally get the answer. So if you were to take a look at the animation here, you break it up, you start to rotate each of these. Now, it's not rotating it all the way around so you can see, but you're rotating these, and look at how that height is going to make the height a little bit taller, and that height will make it a little taller, and that height will make it a little taller. Now, our goal, obviously, is to make an infinite number of rectangles so that this width right here is going to become less and less and less. So we want there to be an infinite number of rectangles where now we have this is the width of each. But notice how the height of each of these is changing. Look at how there's this tiny little gap between these. And now a tiny little gap here, and a bigger gap here, and a bigger gap here. And now way up here, there's a bigger gap. And the reason of these gaps is simply because of the fact that the height is going to change in every single in every single shell. So our goal is find the volume of each shell and add all the shells up. Find the volume of each shell and add the shells up. So let's start with this for a minute, because this is something we have to go back to here and just recognize that there's a little difference between the disk and washer method, which by the way are the exact same method. It's just whether or not there's a gap or not. And I should probably create maybe a little table. Okay, and then the shell method. Okay. So if I were to rotate about the x-axis, or really any horizontal line for that matter, okay? Then I've got to realize that I'm going to have a couple of things here, okay? If I'm going to rotate about the x-axis for the washer method, then that means that I'm going to have vertical rectangles. Okay. And my radius are also going to be vertical, right? Because the radii are basically just are basically telling you what those vertical rectangles are. But what we've got to realize for the shell method is it's going to be the opposite. Okay, it's going to be, and one more thing to recognize here is that these radii are always perpendicular to the pivot. Okay. But then when we looked at it in terms of rotating about the y-axis, about our vertical axis, now we realize that these, just like in a few of the examples, the last two problems that we did on our prior assignment just now, we were going to have horizontal rectangles. And of course, the radii are horizontal at this point. But more importantly, when we take a look back to this disc and washer right here, notice when we were rotating around the y-axis, look at how my radii were perpendicular to where we were rotating, because we were then rotating them around to create these discs, right? So that same thing happens if we were to rotate about the x-axis. So now we realize that in this situation, the radii are still perpendicular to the pivot. What we're going to now notice, though, is that for the shell method, it's actually the exact opposite in every way. Okay? We realize that, first of all, with the shell method, going back to here, now I realize that my pivots over here, okay, I'm sorry, my pivot is going to be the y-axis. But look at how each of these radii now, or each of these distances, each of these rectangles are now going to be rotating around the y-axis. But look at how these rectangles are now parallel to the pivot. These rectangles are parallel to the pivot. That's the most important thing to recognize, and that's really all I'm going to write on this one, okay, is that in this case, I got a question here. Oh, Jose said it looks like a stadium, and it kind of does, except it went down to a funnel in the middle, but yeah, I think you're right. For the shell method, the most important thing to recognize is that the radii, or rectangles, I guess we should probably rename this as rectangles. The rectangles are perpendicular to the pivot. Okay, so for the shell, we just realized that the rectangles are now parallel to the pivot. And this is going to be really beneficial for us, as you're going to see in this next example, because, because then I'm not going to have to break it up into two separate integrals, and oftentimes the integral itself is going to be much easier to calculate. So you might be wondering, well, why are we learning different methods when we should just learn the one that's going to be easiest for us? And the reason is because different methods are going to be easier in different situations. Okay, a lot of times the disk method is going to definitely be the easier than the shell method, but then sometimes the shell method will be easier. Okay, so this is basically what I want to get at about how this works. Okay. Move this again. Okay. So all that's basically happening here, and you saw it in the video last night, so I'm not going to go a whole lot into this, but really what I want to focus on is the fact that you're going to be calculating the volume of each of these cylinders, okay? And so the first thing I'm going to do is that I got an empty toilet paper roll right here. And so hopefully you can see my picture. So if you can't, well, maybe can you see me?
Yes.
Okay. So here we've got a toilet paper roll right here. Okay. It's a cylinder. Picture this as one of these cylinders right here. And then we're just going to have an infinite amount of these cylinders that are, some of them are going to be smaller. And as you move out, they're all going to be increasing in width here, increasing in width. And that's essentially what we're saying here. But don't worry about how big they're getting, because the integral is going to take care of that. The integral is going to be adding up an infinite amount of these shells. We've just got to figure out a formula for one shell. So that's why when we're going to take a look at this volume, the volume of this shell is basically how much cardboard do I need to make this? Well, let's think about that. If I want to find the volume of this shell, not the amount inside, everything inside is a hole. I don't want to see how much I could fit inside of this hole. I want to know how much cardboard do I need to create this shell. Okay? So in order to do that, the easiest way I've found is to cut it down the middle and open it up. And when you open it up, now you should recognize that I have a
rectangle.
Close. It's a rectangular prism because it's three-dimensional. So notice that this side right here is in fact a rectangle, but notice that there is in fact a width to it as well. My width of this paper towel roll is just really, really thin, which is what's going to happen with an integral. They're going to be extremely thin. So all we've got to really do then is figure out how could we determine the volume of just one shell. Okay, one shell. All right, so let's go ahead and draw that rectangular prism. Okay, so let's draw a rectangle. There's my paper towel roll, but it's not quite my paper towel roll because it has a width to it. So when I unravel it, this is really going to be my shell. Okay, this was originally what I started with my shell here that was going to have a particular width to it. Okay, all I've done is I've picked it up and moved it. Okay. All right, so first of all, this thickness right here, okay, is really just going to be the thickness of this sheet right here. Okay. So let me kind of draw with colors here. So, oh crap. Okay. So this width, this thickness is going to essentially just be this thickness right here. Okay. We're also going to need to know the circumference, because the circumference here is what this length is going to be. This length right here is actually the circumference. And if you don't recognize why, take a look at my picture here. When I cut this apart, you could see that this edge right here around the top is now becoming the top of the rectangle. So when I put it back together, that's nothing more than the circumference. So I could see that this right here is going to be the thickness. This over here is going to be the circumference. And now obviously this right here is going to be the height of this cylinder. So there are all kinds of ways that people derive this shell method. I think that Professor Leonard on the video did it a little different than I'm about to do it, but they're all getting to the same place. And so if I want to find the volume of one shell, okay, then the volume of one shell is equal to the circumference times the height times the thickness. And so now we just need a few formulas here. So first of all, circumference is just 2 pi times the radius. Easy enough. The height is going to be, well, just whatever the height is, 2 pi r times h, times the thickness. Now I'm just going to go back to here real quick and tell you, what is the thickness going to be? Well, because it's going to be the width of this red one and the width of the blue, and the width of the orange and the width of the green and the blue and the orange and the purple, notice we want an infinite amount of those. So what is the thickness of each one of those going to eventually become?
Dx.
Dx, exactly. So why don't we now just go ahead and recognize that the thickness is going to be dx. Okay. If they were horizontal rectangles, then it would of course be dy. Okay, well now we need to think of this in terms of this picture down here. Okay, so let's look at this and see how much of this I can erase. Because I want to erase most of it. Erase everything, great. Okay, so looking at what we did with the disk method, this was a little tricky because we ended up having to break this up into two different parts right in the middle. And then we had to have one radius that was horizontal going this way and one radius that was horizontal going this way. This is where the shell method can be beneficial because we don't have to do that. Instead, let's get each of our radii to now be vertical. Each of our rectangles to now be vertical. And when I rotate this around, it's going to create this shell, and I'm going to create a bunch of those shells. So let's think about what we mean by the radius here. What is the radius? Well, let's look at the radius. The radius is nothing more than just the distance from the pivot to wherever I am, okay? From the pivot to wherever I am. Well, look at what this is. It's easier to see on the x-axis. From the pivot to this location is nothing more in this case than just x. If the radius that or if the rectangle happened to be over here, notice that that distance right there would then be, again, x minus 0, wherever this x value happened to be. And so that radius is really just going to be, again, right minus left, but it's really going to be either x or x minus. If the pivot was somewhere other than 0, then it would be maybe x minus -1 or x minus 2 or x minus -5 or whatever it is. But notice that in this case, this is just 2 times pi times x minus the pivot. In this case, the pivot happens to be 0.
Professor, I have a question.
Yeah, go ahead, Dylan.
So, when, like, let's say we're doing an actual problem, would x just be given to us at the start of the equation, or would we have to find what x is?
Do you mean this x right here?
Yes.
No, x is x. X is x in the formula, and that's what's beautiful about it is you just put x.
Oh, okay.
It is just x. X is going to change as I move from 0 all the way to 2, right? Notice that at each of these rectangles, my x value is going to change, but that's accounted for in the formula for the radius because each of these x's is going to form a wider shell. And so that's why we're basically saying add up an infinite amount of these where x is just x, okay?
Okay, thank you.
Yeah, sure. So we'll set up a problem, this same problem in a minute and see how it's easier than the disk method, okay? All right, but we now need to know what the height is, right? And so now we need to figure out what the height of this function is. So how do we figure out the height of this shell? So we already know the radius of the shell is going to be x minus the pivot, which in this case is x minus 0, okay? We already know that the width of this shell, look, the width is just literally the width of that little piece, which is so infinitesimally small that we refer to it as dx. But what is the height of this shell then?
From the video, it was saying that the height is the original function.
Yes, it is. Take a look at this. Isn't the height just now top minus bottom? And isn't the top just the function? So notice that in this case, the height is nothing more than just, and I'm going to change this color so that we can follow along with the colors here, times the height. So the height is nothing more than just the function minus 0, which is really just the function. It's not always, I guess I'm going to say it's the function, but in general, I'm going to just tell you that it might not always be the function because it's really just the top minus bottom. But in this case right here, it's the function because of the fact that the bottom is 0. Okay. And lastly, dx. So now we've got a formula for the shell method. The shell method is nothing more than an integral. Shell method says that the volume is equal to 2 pi times an integral. Unlike the washer method where the coefficient was pi, this is 2 pi simply because we're dealing with the circumference. That's why it's a 2 pi. We're going from A to B, where these are going to be dx values, right? And now we realize that all that we have inside is just going to be x times what?
The function.
The function. And that's it. That's your shell method. Now, sometimes this could change. Keep in mind that as I mentioned earlier, it might not always just be x. If it said I'm going to rotate around the line x equals -1, then look at the radius. The radius would then extend from here to the outer edge of the shell, which would mean that that radius would be x minus -1, which would be x plus 1. So that would change this x into x plus 1. So just be careful with that because sometimes it's not just x, but that's why it helps to draw the picture so you can see where the pivot is, okay? Now, if you were rotating around the y-axis, or I'm sorry, around the, this is, if you were rotating about the y-axis, right? But if you were rotating about the x-axis, notice that now you would be going from C to D of y times whatever the function of y is, dy. And that would be about the x-axis. So you could see that what we've just done here is if I'm going around the y-axis, I'm doing dx, but if I'm going around the x-axis, I'm doing dy, and that's going to bring us back up to the top and show that there's one extra difference between the two, okay? In this case right here, if I'm doing the disk method around the x-axis, this is going to be dx. But if I'm doing the shell method around the x-axis, this is going to be dy. Likewise, if I am doing the disk or washer method around the y-axis, then this is going to be dy, while this will be dx. And so I'm ready to do this last problem again. Only now let's take a look at how this is going to be a lot easier. Okay, so now let's set up the shell method, really. Okay, for the shell method, we are now going to say, well, with the disk method, I had to break it up into two separate pieces. I'm going to say, forget that. Let's just do the shell method and do one piece. So now this is going to be my representative rectangle. So for the shell method, my volume will be 2 pi times the integral from 0 to 2. Because notice I'm extending from the left side all the way through until the right side, which is why we're going to have our integrals from 0 to 2. Okay. Well, now I know that I need to figure out my radius. Remember that my radius is going to look something, this is going to be my shell right here, right? So my radius is going to extend from the pivot to that rectangle. That's just x. So I just write x times. Now I got to find my height, but notice that my height is nothing more than just f of x. It's f at whatever this particular x value is. Now in this last problem, you might remember that this was the function y equals 1 over x plus 1, which is why over here, all we need to multiply by is times the function 1 over x plus 1. But finally, the width of this, remember the width of this, there is an infinitesimally small width, but that small width is nothing more than just dx, which means all we're integrating is the function x over x plus 1, which can be done with u substitution. So look at how this integral using the shell method is so much easier than doing the exact same problem using the disk method. I mean, look at this. Look at this integral right here. One single integral of x over x plus 1. Simple u substitution. Go back here to this problem, and now take a look at the integral. We had to break this up into two separate parts. We had to write it as an integral from 0 to 1/3. We had to figure out that this value right here was 1/3. We had to break it up from 0 to 1/3 and then 1/3 to 1, two separate integrals. We had to figure out what the first radius was and the second radius. We then had to integrate two separate integrals. And that's before ever evaluating this. Now I've got to plug in 1/3. I got to plug in 1/3 into here, into the ln. It just becomes really ugly and nasty and difficult. Instead, don't do it. Instead, do the shell method. So this is the benefit of doing the shell method. It's just a different method that sometimes simplifies finding volume of shapes that are difficult using the other method, okay? And sometimes the shell method is worse, so don't do that, and that's why the washer or the disk method could be easier. I'll stipulate on the test which one I want you to use, just because I'm testing on a particular method, but in practice, it really doesn't matter what method you use. You just normally want to use the easier of the two.
So could we can you use the shell method if there's a gap, like instead of a washer method?
Absolutely, you can, yeah. Because all that's gonna, if there was a gap, let me just show you basically what would happen now. If there was a gap, let's say that this right here was the pivot. Okay. Notice that the region would still be the same. Okay. The region would still be right here. So I would still be integrating from 0 to 2, right? It's just that every single, the shell here the first shell I would use would be this big. That would be the first shell I would use, right? And then the largest shell I would use would be this big. Okay. But notice the difference between these is that there would still be a gap in the middle because I was only going from 0 to 2. So that wouldn't cause an issue. Okay. And lastly, if there was a, so one more thing, if there was a gap, then notice the radius would no longer be x. The radius that extends from the function wherever I'm at, wherever the shell is going to be, is now going to be this long. So the only thing in this formula that would actually change is that the pivot is going to be x and an extra 1. So this x value, or this radius, would now be x plus 1. So the only thing that would change would be this thing, which would become x plus 1, which would be interesting because that would be even easier to integrate since it would be x plus 1 over x plus 1, which is 1. So yeah, you could absolutely still do the shell method even if there's a gap. Okay, where the washer method would have been used before, now you have oh, and the washer method, can you imagine? The washer method would have been insane on this problem, because you would still have to break it up into 2 separate pieces, right? One below this line and one above this line, but you'd have the right minus left in both of those as well, and this would have just been insane with the washer method. So yeah, good question.